Okay, so yes, ladies and gentlemen, welcome to this week's monsoon seminar. And our speaker this week is Yama Dixit from the Indian Institute of Technology in Delhi. Yama did her PhD at the University of Cambridge and then a postdoc in France and another in Singapore. And she's recently started a new job back in her home country, and she's going to tell us all today about the Indian monsoon after the last glacial. So, Yama, without further ado, please take it away. And if you want to ask questions, put them in the chat, and I'll call you at the end. Thank you.
Thanks, Peter. Well, I've given this talk before. I don't know who all are seeing it once again, but this talk would be about what do regional records tell us. So I'll be talking about lake records, essentially from northwest of India. There are several lakes which have been studied, and I did study some of them myself, but to kind of interpret it as all of them as recording Indian monsoon history, we might have to be critical about how to interpret signal. So I'll talk about all these lakes, including my work in the region, and then basically look at how monsoon has evolved from the last glacial period over the entire Holocene. So we all know, we've been talking about monsoon. It's the seasonal migration of ITCZ and energy transport. And when you talk about Indian subcontinent, there are two branches, the Arabian Sea branch and the Bay of Bengal branch, which kind of bring distinct moisture, which have distinct signal on the Indian subcontinent. So this seasonal migration and southwest winds, they kind of introduce these kind of seasonality, and you can see that June, July, August is August, September are the main monsoon months over the Indian subcontinent just after summers. So I won't go into detail because this has been talked, and these are monsoon series, and I think almost all of the talks start with this. So I'll just leave it at that. But what I'll talk about is this region that you see. So this is in northwest India, and I'll be only talking about the continental lake records from in and around Thar Desert. So this is Thar Desert that you see in the picture on your left, and there are several records that have been studied. So Sambar Lake, Didwana, Lumkronsar, these have been studied, work started in early 70s, and Singh et al. Did pollen work in these, but these lakes were not very well dated. So it was difficult to sort of interpret and understand the Holocene history. But, and then subsequently, Saini and including me, we worked on lakes like Kotla Dahar, Rivasa, and Karsandi. So in terms of kilometers from east to west, it's only about 150 kilometers, but then the region and the climate history that they're recording is really diverse. So there's this, if you go from east to west, there's a precipitation gradient, and it's not, if you can see these numbers here, these are precipitation isoids, and you can see that, it really varies, and there's a sharp gradient in terms of precipitation, and it lends a distinct sort of character to the region, and the sedimentology, geochemistry of the lakes in this region. And if we just talk about Kotla Dahar, Rivasa, and Karsandi, it really changes drastically, even in a matter of 100 kilometers. So that's why I chose this region to study. And before delving into past climates, it's essential to understand what is the oxygen isotopes and what is the modern climatology like in the region. So the temperatures in the region, so this is again we don't have any isotopic data or data from here. So we take the nearest GNIP data, which is New Delhi, which is about 80 kilometers from Kotla Dahar. Now Kotla Dahar is in a state called Haryana, which is southwest, slightly southwest of Delhi. So if you can look at the monsoon months, clearly July, August, September has the highest rainfall, and in terms of temperature, it averages around 30 degrees, 32 degrees. And oxygen isotopes, you see that it varies. It has a very sort of seasonal character, and weighted mean is about minus 5.9 per mil. So this gives us a fair picture of what we would expect in the carbonate, in the oxygen isotopes of carbonate that we have, that I would be showing, the results that I would be showing in the next few slides. Now, this region is also interesting because this region, which is now not so populated, was during the Bronze Age, like 5,000 years back, was one of the most densely populated region in the across the globe. So the orange dots that you see here are all archaeological sites. So this civilization was called the Indus Valley civilization, and this civilization was contemporaneous with Egyptian civilization and also Mesopotamian, and the civilization had trade, and it was quite evolved civilization. And it was spread all around the Thar Desert region. So now this again underlines the importance of these lakes, which are right in the vicinity. I mean, for example, Rivasa is very close to one of the urban center, which was one of the major cities of this civilization, Rakhigari. So looking at these, if looking at the climate history that can be kind of inferred from these records, we would be able to kind of say how the civilization would have evolved in these kind of changing climate to the last 5,000 years. So that's why these lakes were chosen. So the lakes that were chosen is Kotla Dahar, that is in the subhumid region. It receives about 600 to 700 millimeters of rainfall annually. And then the semi-arid region, Rivasa, which is sort of at the borderline of Thar Desert and the humid plains, Gangetic plains to the east. And arid Thar Desert lake, again, this is not in the center of the Thar Desert, but just when Thar Desert sort of ends, it receives less than 400 millimeters of rainfall, and it's called Paleo Lake Karsandi. So in terms of proxies that I've used for reconstructing these records, I've used these shells. Now, this is a gastropod shell. It's a snail shell, and the shell is basically aragonitic. And I've used the oxygen isotopes of this aragonitic carbonate shell. And I also used ostracods. And ostracods calcite, again, if they precipitate the carbonate in equilibrium with the lake water in the lake in which they were living, you can sort of get the lake water isotopes, and also at what temperature they were sort of precipitating their shells. So oxygen isotope of these carbonate shells is dependent on the temperature and the oxygen isotope of the water in which they are living in.
It's okay, Yama. You're muted.
I just went.
That's okay.
Is that all? Okay, sorry. So, can you see me now? It's okay.
Yes, everything's good.
Okay, so you can see, so because of this Rayleigh fractionation, you can see that, for example, during wet periods, you have heavier isotopes being precipitated, also known as the amount effect, and the oxygen isotope in this one decreases. And similarly, during high EYP or high evaporation, the lighter ones get evaporated first, and the oxygen isotope value changes. So high oxygen isotope, as a rule of thumb, we can say that it's cold and dry, and lower oxygen isotope values would be warm and wet periods. Now this is not so straightforward. This is an equation that can relate these two So you can out if you have oxygen. This is the measured value of these carbonates, and oxygen isotope of water. If you can, another variable to kind of reconstruct this oxygen isotope of water, you can reconstruct temperatures of the past. Now, sorry, I'll just move the picture here. Now, in arid environments, we might not have these shells present. So for those environments, we use other proxies, and one of these proxies, which which Professor David Horrell at Cambridge has been working on, is gypsum hydration water. So what isotope of this would give about reconstructing temperatures, we could get oxygen isotope of calcite from these shells, carbonate from these shells, and oxygen isotope of water if gypsum is there from gypsum hydration water, and then we could actually sort of reconstruct temperatures. Now, there are a few exemptions, of course. So one of them being that both gypsum and should be precipitating out in equilibrium with the lake water isotopes. And also that there was no exchange in oxygen isotope in both carbonates and this hydration water. And of course, there's a kinetic fractionation involved. And if we correct the oxygen and as well as hydrogen isotope by the kinetic fractionation that's involved, we can get the exact lake water oxygen isotope from the hydration water in arid environments. So these are the proxies that I've used, and I'll show you the results now. So the first lake is in the subhumid region. So this one, Kotla Dahar in Haryana. And what you see here are three panels. So the first one being weight % calcium carbonate. On x-axis, we have weight % calcium carbonate, oxygen isotope in permil, and also Ostracod count. Now, the reason why I've used Ostracod count and not isotopes of Ostracod is that the Ostracod were sort of disappeared. Ostracod disappeared after a point, and I could not get a continuous record. So Ostracods are very sort of good species in terms of they change with changing salinity. So the species changes. So I use them as salinity indicators. So again, it's very qualitative. I'm not like quantifying salinity as such, but then qualitatively, if it was a freshwater or sort of saline or a drying sort of lake. So coming to the record, it spans from 0 to 7 kiloyears. So you see that weight % calcium carbonate kind of average around 70% between 6 and 6.5 kiloyear BP. And this was also the time when the oxygen isotopes were quite negative. Now, negative would again indicate that it was sort of wet period, or if we kind of interpret in terms of hydrological changes, the E by P was really low, so less evaporation and precipitation was high. And in terms of the species of ostracods, you see these thin-walled freshwater ostracod species. So clearly, this was the wettest phase in the region, or we call it the deep water phase in the lake history. Now, after about 6 kiloyears and up to about 4.2, we see that there's a gradual decline in weight % calcium carbonate, and also sort of increase in oxygen isotope values, averaging from -4 to about averaging from about -5 permil to about -3 permil. So this change or this shift in positive values indicate like drying or sort of shoaling of the lake. And this change in species to this relatively robust shelled Cyprides turosa indicate that this was, now this species here can withstand salinity up to 60 permil, so 60 PSU. So this is really like saline water, and this is also found in relatively in desert regions where the waters are really rich in salts. So So this change in species also indicate that this was a shoaling phase or sort of, gradual drying phase. Now, there is a 4 per mil change in isotopes at around 4.2, and it goes up to around 3.9 kiloyears. So beyond which, the weight percent calcium carbonate comes down to about 10%, and oxygen isotope also averages about 2 per mil. Now, from -2 to about 2 per mil, there's a change of about 4 per mil, which is huge if we sort of convert it into temperature. It's about 16 degrees of temperature change. So clearly it's not temperature because, temperature hasn't changed that much in Astolfos, in this region. And if you look at the ostracods are absent. So this abrupt drying that we think, and beyond that, ostracods are not present. And there's also a shift in the oxygen isotopes of this gastropod shell that was used for reconstruction. So, and then it continues to present. So what we call is this as ephemeral lake. So if we go there now, it would be completely dry, and there's like people growing vegetables and basically used for agricultural purposes. But like it gets filled up during rainy season, so it's sort of an ephemeral lake now. And these ostracods cannot withstand drying. So that's why the ostracods kind of after a point they are absent. So after 4.2 abrupt drying or dry that was centered around 4.2, the lake dried up and became ephemeral, and it kind of continues to be a seasonal lake till present. So in terms of this has been the 4.2 kiloyear edification event has been talked about a lot, and this figure is not updated. I mean, there's still more data and a lot of papers are available, but I just wanted to show you what I had done at that point of time. And this is published in Geology, and a lot talked about paper. And what we thought was that this change in 4 per mil change in gastropod oxygen isotope kind of, in terms of timing coincides with something that was seen in Mamluk Cave speleothem. So this drying was also seen, also talked or mentioned in the paper by Stoffwasser and foraminifera oxygen isotopes. So you could clearly see that this change or drying was kind of, from Arabian Sea to Northeast India, and this is from Northwest India. So it kind of was widespread and not regionally recorded in our lake. From Gulf of Oman, there's evidence of dolomite dust concentration peaking, which sort of, indicates increased aridity around this period. And also from Kilimanjaro ice cores, there's a dust peak and oxygen isotope changes around that period. So it was sort of regionally widespread event, and it's usually attributed to increased El Nino events around that time. And there was this paper that came out that, about after the 4.2 event, El Nino, increased El Nino event, because of the increased El Nino event, there was a hiatus in coral population in the Pacific region. So this is thought to be one of the kind of, that contributed to weakening of the Indian summer monsoon. But also there's evidence that the impact of ENSO on the monsoon rainfall was sort of modulated by what was happening in the Indian Ocean in terms of Indian Ocean dipole. So both of these factors are thought to have, been instrumental in causing the monsoon to weaken at that point. Now, it had implications. Archaeological records suggest that this was the timing when mature phase of around that time, mature urban phase of Indus civilization was sort of ending, and the late urban phase was beginning. And this was also the beginning of a population leaving the urban centers and going back to village based settlements. So this event, archaeologists are still working on, how and when the Indus populations sort of behaved or responded to this 4.2 event that has been recorded in a lake which was very close by to the populations in these populations. So so this is again not a regional event. This was there's the paleoclimate evidence of this drying for Mesopotamia and also for Egypt, from Egypt. So I mean, all these three civilizations, Bronze Age civilization, have been somehow sort of thought to have been related. The cultural evolution of these civilizations are thought to have been related to the 4.2 drying. Now I'll come to the next lake, which is Paleolake Rivasa. Rivasa is in the subhumid region, and it's at the border of Thar Desert. So it's in the semi-arid region and the border of Thar Desert. Now, what we did here was we were trying to get a pit sort of dug to get a complete sediment section, but then we got this exploratory sort of well, and this was done for some other reasons, but then we could see a clear evolution of sediments from Aeolian sand. It's not very clear in the picture. The well was very narrow, like the diameter was very short, so we could not take a proper picture, but you could see that this sand here at the bottom, and we have an OSL date from these sands, and this dates beyond 11 kilo years. So clearly the glacial periods, and this was there was a sand dune in this region, and this region was basically covered by sand dunes at that point. Now we also got other pits and sediment section dug around the region. This lake was quite widespread and shallow lake, but area-wise was spread out. I don't remember how many kilometers square, but it was quite wide. So clearly the lake did not appear until about 11 kilo years, and after 11 kilo years, you can see these black dots. So these dots are oxygen isotope measurements on ostracod called Cyprides torosa. So these ostracods started to show up. So we measured oxygen isotopes in these ostracods that show up, that were there. And in green, we have oxygen isotope measured on the shell that I just showed, on the gastropod shell. So this is Melanoides tuberculata. And so after about 10.5, these gastropod shells also beginning to show up. So the sediment also changes in characteristics. So from sand, it kind of transforms to shelly silt, and from shelly silt, it transforms to really massive calcareous shelly deposit. This is fully encrusted with both gastropod and ostracod shells. So in terms of isotopes, you can see that there's a general sort of negative values, trend going towards negative values, which indicate that the monsoon is sort of increasing, or the precipitation in the region is increasing. Now, if you look at the timing of this, you can see that the highest or the wettest phase, or the oxygen isotope was most negative, was around between 9.5 to up to around 8.2. So at around 8.2, there was this distinct 10 centimeters of hard ground. So when I say hard ground, it's more like a Bacchus stone, and really root. You can see that there was like root, but encrusted. This was basically a clear indication of desiccation of the region after what was thought to be a deep permanent marl lake with full of shells. So the lake, from Aeolian to shallow ephemeral lacustrine, and then from shallow lake to a deep permanent marl lake, as you can see in the sediment, at around 9.5, and then complete desiccation at around 8.2. This evolution was really interesting to see. And then, and this is an abrupt weakening that we think was caused because of continuously aerially exposing these marl sediments, and then this aerial exposure was sort of this led to the complete desiccation and formation of hard ground in the region. So I was literally like standing here and sampling the sediments above this hard ground. So it was a proper slab sort of a structure. And beyond that, there is ephemeral lacustrine sediments. Ostracods they do appear, and in black here. So you see the measurements are there, and then also there are shells with gastropod shells, which we've measured for oxygen isotope. Now, in terms of sediments, these are silty sands that appear after the hard ground. Now, this lake, this record terminates at around 6.2 kiloyears, because I think there was some sort of agricultural activities and they kind of removed the topsoil. And there was so I didn't use the top 15-20 centimeter, which was reworked. So so beyond that, I think they had removed the top part, and we could only go up to 6.2 kiloyears in this lake. But what is interesting to see is that the lake appeared after the last glacier period, and then it has a clear early Holocene monsoon intensification with these permanent Marl Lake sediments, and then an abrupt drying around 8.2, and the transition to an ephemeral lacustrine lake. So again, this 8.2 event is the most prominent event of the Holocene period, and this was the largest climatic excursion in terms of Greenland temperature change. It changed by 3 degrees, and greenhouse gases concentration, methane declined by 80 ppb. So this cold event is clearly recorded that you can see in the first graph here, first plot. So you can see this oxygen isotope of ice cores. In North Grip cores, that the dip is basically indicating a cold event or colder temperatures. Now, this is also seen in a percentage of G. bouloides, and this from Arabian Sea. So in terms of percentage, there's a dip in the number of foraminifera shells that is there in the Arabian Sea. Now, this is work by Gupta et al. And then other caves in South China and South Oman also have this sort of a double dip structure that they call it for 8.2 drying of or monsoon weakening in the region. And our hard ground that we see in the lake also kind of centers around 8.2, and we think it is responding to the North Atlantic cold event, as all the other records of monsoon are. Now, I mean, there is increasing evidence of 8.2 from around the globe. Again, this is not an updated plot. This I have taken from one of the talks that I gave, but there are I mean, I'm working on it, and there are the map is now fully populated, and there are several lakes, marine ice core, speleothem, and a peat record. But when we did it, it was the first evidence from the Indian subcontinent. There was nothing, and even now, they're not, Indian subcontinent doesn't show much of 8.2, but there's evidence from China, as you can see. But now the map is really populated. So 8.2 event did have impact. And my recent work in Singapore, in sediments, margin marine sediments just off Singapore, also has this 8.2 signal, which I'm writing up. And so clearly it did impact the entire globe. So now that brings me to my last lake. This is the Lake Karsandi, which is in the Thar Desert. As you can see from the sediments on the right, the white color massive sediments that you see are gypsum. Like this is 99% pure gypsum, and this has alternated sand deposits in between. So if we look at the litholag, you have orange gypsum deposit, and it has sand deposits as well in between. Now the problem with this section was that the top this was under a sand dune, so they were mining it for gypsum, and that's how we got a nice cleaned up wall of lake deposit, and which we could sample for analysis. But the problem was they were not much to date, so we could date the top sand for by using OSL technique, and also the bottom of the sand, because there's this sand at the bottom, aeolian sand that we could use for AOSL. But other than that, there was not much to date in terms of carbonates. So So I mean, if we look at the broader picture, we can see that the lake appeared sometime after the last glaciation, and after the last glacier period, you can see that the lake appeared. There's gypsum being precipitated out of whatever waters that were there, and it ended sometime before 3.2 kf. Now, what we had was this unit, this sandy unit. Now, this sandy silty unit had some shells, gastropod, ostracod, and this unit had some charophytes. So charophytes are plant algae-based calcretes, plant-based carbonate, basically, which we thought we could date because there was nothing to date. So but we'd still take it with a pinch of salt. So this date 7.5 here. This comes from charophyte garragonite from this unit here, unit 6. And all the other dates are on shells from this unit, unit 3. Now, we were not too concerned because the aim of this work was to look at the civilizational changes around this period, around 5,000, 4,000, like, in that time interval. So we started focusing on this event, this particular unit, unit 3. Now, so in terms of the proxies, I used oxygen isotope of gypsum that was precipitated. Now, gypsum was also present in these sandy or sandy units. So we picked out gypsum, extracted water, measured oxygen and hydrogen isotopes in them, and also calculated the dxs. Dxs is a derived quantity from derived variable from oxygen isotope of and hydrogen isotope or deuterium isotope. And dxs basically is an indicator of relative humidity. So it would indicate that what was the evaporative conditions like when these gypsum was being deposited. So if it's positive, it would indicate that the precipitation of gypsum was happening during a higher relative humidity, which sort of is an indication of a wetter period. So, and then we also had percent detrital, and clearly percent detrital percentage is highest in this unit 3. This is because of the during wetter periods there was more detrital that was coming in from the watershed and from the region around it in the lake basin. So that's why you can see more detrital in this part in unit 3. And in terms of oxygen isotope, the lower values in oxygen isotope and also lower values in deuterium isotopes indicate that this was a relatively wetter period. Now, if we focus on this unit alone and look at the ostracod that was present, I mean, there were not many, really scanty, but then whatever ostracods that were present, it was just in this unit. And because ostracods need water, this unit was the wettest unit. And in terms of date, this unit dates around 5.1 plus minus 0.2, so around 5,000 years. And then the highest sort of precipitation or highest amount of highest number of ostracod that were seen was around 4.4 kilo years or 4,400 years. Now, this is the timing of when the early Harappan kind of transformed to mature Harappan. And the urban phase that, if you look at the map, the urban settlements that you see here in orange were all around Thar Desert, but post-urban phase, so post 3.9 kilo year PP, you see that all these settlements are sort of clustered around on the eastern part. So there was sort of an eastern migration of sites that happened after 3 kilo year PP. Now, we do not know when this unit or this kind of wet period ended, but it ended sometime after 4.4 and sometime before 3.2 that we have the OSL date on. So abandonment happened sometime in this unit. But then you can clearly see that the highest precipitation period, or like when this region was wettest, this the timing of the wet period and the transformation of early Harappan to mature Harappan sort of coincides. So it sort of fit. Archaeologists really like the fact that this region received higher rainfall at the period when Harappans were thriving in the region. So so that brings to the end of these three lakes. But how do they fit in with the entire local history? I mean, there were several other lakes which have been worked and studied by other scientists. And so what I did was I plotted all the lakes that I talked about. So there's this subhumid lake that I just showed, semi-arid, and tried to kind of work on same age model using the dates, and then the resulting plot that you see here is this. So these are the Thar Desert lakes. Karsandi is the one that I just showed with sand deposits. So to takeaway point from these this sort of compilation and collation of records is that most of the lakes in this region appeared after the last glacial period. So sometime around 12 kilo years, these basins started to fill up when the monsoon responded to increased boreal insulation. And after that, there's really like divergent early Holocene history. So so you see that Rivasa was sort of slowly picking up, and it was it was at the high stand in the early Holocene, but Thar Desert was really ephemeral at that point. So what I kind of, in the way I interpret it, is that because of high evaporation and precipitation rate, because the insulation, mind you, in the early Holocene was still relatively higher as compared to as we go into the Holocene to present. And the lack of large drainage basin in these lakes kind of led to ephemeral lakes in the Thar Desert, while the lakes here in the eastern part were still getting rain and relatively more rain because of the precipitation gradient, and the basin was the drainage basin was quite large, which kind of supported this sort of high lake stand in the region. Now, between during the mid and late Holocene, you see that now the lakes in Thar Desert show like really high lake levels. Even in Karsandi, you see that it's the mid and late Holocene that the lakes have high stand. So what we think is that because of the lower evaporation and precipitation rate, because of the decreasing insulation, boreal summer insulation, and so there's a net increase in effective moisture because of lower evaporation during these times. And again, we have evidence, which I'll just show you, that there was additional moisture coming from northeast in terms of winter monsoon, which kind of fed these lakes in the Thar Desert and led to a high stand later or in mid Holocene region. Now, and then there is this progressive drying. So you see this lake, so the lakes kind of dry up first in the western part, and as you go towards east, so red dot are basically drying of the lakes. And you see that there's a progressive drying following the monsoon gradient, which kind of which is from east to west. So so it kind of fits in the general interpretation now. So what about the abrupt climate events? So so if we look at the lakes Rivasa and Kotla Dahar, now taking out the lakes that I talked about, so in the lakes that I showed from the Thar Desert region, and just talking about Rivasa and Kotla Dahar, and put them with other records, which are sort of now, I mean, there's so many records of monsoon, but what I've taken here are only the records that are, classic records and have been cited a number of times, and for the lack of space. But then we can put in as many as we want. But then what I've used are like really classic Donghae Cave record, Poonf Cave from Oman, Foraminifera stopwasser, because it was the first paper who kind of talked about Indus civilization and evolution with monsoon. And then there is also this paper by Gupta et al. From Western Arabian Sea. And this is Bay of Bengal Foraminifera data. And also leaf wax data from Bay of Bengal. So what we see is that generally the lakes and speleothem respond to the longer term monsoon strength corresponding to the Northern Hemisphere summer insolation. But there were abrupt events like this 8.2, which is seen as the hard ground, and 4.2, the 4-pole mill change that we see in Lake Rivasa. So I've put them together because this Kotla Dahar doesn't go beyond 6.5, and this one doesn't go like to present day. So I put them together for the ease of plotting them. So, but there are other events like 5.9 to 6 and 9.4, 10.4, and 11 that is clearly recorded in Rivasa in terms of the way the lake has evolved over time. And these, if you kind of zoom in, you could clearly see that these events were also recorded in the cave records from Oman and China. So when this is a paper by Geshe et al. And what they talked about is they looked at what was the winter monsoon strength like. So when I talked about winter monsoon increasing in the mid to late Holocene, or they were the reason for higher lake stand in these Thar Desert lake. What the Geshe et al. Did was they looked at N. dicatri, which is a foraminifera, thermocline dwelling foraminifera, and what they see was is the oxygen isotope. And the way they interpret this oxygen isotope of N. dicatri is that this blue peak that you see before 4.2, basically between 4.5 and 4.3, this is the increased winter monsoon rainfall that N. dicatri isotopes are depicting. So period of increased surface water mixing that happened around this time was because of increased winter monsoon. And around 4.1, both the winter monsoon and, as you can see, this stark change in Kotla Dahar, they all indicate that there was both in summer monsoon and using this evidence from Geshe et al. In winter monsoon kind of decreased after around 4.2 Ka. So so to look at the bigger picture, if I plot Rivasa and Kotla Dahar on the same axis, and they sort of complement each other, looking at gastropod oxygen isotope values, there are several abrupt events that kind of mirror, the timing of it mirrors in terms of what was happening in the Greenland. So, for example, this 4.2 event, 5.9, 8.2, 9.4 clear isotopic excursion, 10.4, and 11 when the lake sort of appeared. And again, ANSO variability is sort of also linked with the ISM variability in around 4.2 and in the timing that followed. So these events that were recorded in the lake Kotla Dahar and Rivasa looks like, it's not a regional history, but there are the Indian summer monsoon was sort of was sort of teleconnections with the North Atlantic climate. Now these events have been identified in the new geological timescale, and again these are recorded also in the subhumid region and semi-arid region lakes that we studied. Now, So yeah, so I'll just conclude this here that the paleoclimate records from Northwest India do provide compelling evidence of significant regional differences that you see in the timing of monsoon responses to orbital forcing. So it's not it's not quite straightforward to just interpret the lake records as monsoon records, even if we know that there's this Arabian Sea branch and Bay of Bengal branch feeding the northern part, the northwest part of India. But only the subhumid to semi-arid or Kotla and Rivasa indicate the gradual monsoon weakening and sort of, are in line with other records from far field regions, Oman and China, and, marine records from Arabian Sea and Bengal. But other arid Thar desert lakes contain regional hydroclimate history. So these records clearly demonstrate that it's not appropriate to examine the impacts of past and future climate changes on societal transformation in the entire region based on an oversimplified global monsoon signal, so as to say, and also, or just from one regional climate record. So we need more records from the region to kind of clearly understand how it was, how the regional climate history has changed and how it would have impacted the past societies. So I'd end with thanking several people who have been involved in this work, and including my PhD supervisor, Professor David Hoodell, and also the archaeologist, Dr. Cameron Petrie, and others who have been involved in this work one way or the other. So yeah, thank you.
Oops. Thank you very much, Yama. Let me see. So if you'd like to ask questions, you can either raise your hand and I'll call on you, or you can type a question. I see we have one from Tara Janelle. Tara, do you want to ask your question?
Sure, I'd love to ask my question. So I'll just kind of read off of what I wrote into the chat too. But anyway, great data, Yama, and lovely talk. So I guess I was curious about some of the spatial extent of some of these lakes, because I know that some work has been done in other parts affected by the South Asian monsoon and East Asian monsoon, looking at how the relative expansion and contraction can tell you about the hydroclimate for the region. And because you have so many lovely lakes that are across this precipitation gradient, I was wondering if it was possible, if there was evidence that existed, that you could use that with some of your data to kind of showcase how the precipitation gradient has changed through time using these lakes. Yeah, anyway, so it's like half comment, half question.
No, thanks, Tara. That's a really good comment. And now that I'm starting off as sort of an independent PI, and one of my objective is this, that, to sort of map around and look at the spatial extent, because, just these three lakes with really divergent sort of story to tell, I really need to kind of, map the region. There's several lakes in the region. I mean, the basin is kind of filled up, but the story is different. So I mean, that's something I plan to do. I would like to map the spatial extent in the region, and there's a lot to do. Yeah. So, I mean, I do not have an answer to that, but yes, I mean, that would be a very cool thing to do, and I plan to do that. I mean, I'm starting. I mean, it's very close to Delhi, so going to Haryana would be a day of field work. You can come back. So that's what I plan to do actually with my students. Yeah.
Excellent. That's great to hear. Awesome.
Yama, there's one thing I didn't really understand, and I just wonder if it's just these regional differences you're talking about. So, at Kotla Dahar, you show this change from it being essentially quite wet, and then it gets dry around 4,000 years ago. And you were showing these other records where there's this dry spike, but yours isn't a spike, it's like a step. And I just, is it that other places are only dry for a little bit and then go back to being wetter? Or, I mean, do you know, or is it just because it's very intense at that time and short-lived? Can you say something about that, please?
This is such a brilliant question. And I've been asked this question, I was asked this question when I was writing this paper for geology. and they were not ready to accept that, this is a 4.2 signal, the reviewers, and which is a great point. So the way the lake records work is really different as when we compare to, like, for instance, say Speleothem or a dust peak, and which you've picked out very well, that all these are peaks, while in lake it looks like a change in steady state of isotopes. Now lake water, if you would imagine lake as like a beaker of water which has some isotopic value, like a container of water which has some isotopic value, and there's some water, or some water of different isotopes feeding in the lake, and lake water is constantly changing because of the evaporation and what is coming in. So let's say there's let's say the lake water is about -2 per mil oxygen isotope. But if the lake, so this event, if you look at the peaks, existed for about 200 years, this drying event. So let's imagine that for 200 years, the monsoon precipitation in the region sort of weakened. I mean, it was not like every year it weakened, but it was for 200 years with relatively weaker as compared to before, prior to this 4.2 event. So the oxygen isotope that was coming in the lake water, which has like this constant of -2 per mil isotopes, oxygen isotope would be really like different, that would feed in. And it would change the the resulting isotope of, after that event or after that 200 years is gone, it would change the isotope of the lake water, which is what you see.
Okay.
So there's like one steady state, 200 years of some other sort of, isotopic value of rainfall, and then another state of, another steady state of lake, which has different isotopes. So it essentially, while writing this paper, we did made a like simple conceptual model, model of how lake, even simple 10% decrease in monsoon rainfall would make drastic changes in the lake water isotope, which would be recorded in the isotope of these shells that you see here.
Right.
So the way it is, it is an event, but the way you see it is the steady state that has been changed because of this abrupt sort of event, rain isotopes that happened for 200 years. If you see, I mean, if I show you the model, you would be, I'm yet to publish that, because this question has been asked to me several number of times, and we didn't publish that yet because we thought that would kind of entail a different sort of isotopic system and paper. But then it's a very valid point. When you look at the record as such, I mean, it looks like it's a really different sort of record, but then 200 years of changed rainfall would change the isotopes of the system, and that's what you see here. If I don't know if it's clear.
Thank you. So I'm going to ask a question here for Dolce Oliveira. She can't ask the question because she hasn't got a microphone. So the question is, she says, the abrupt 2.8 Ka event has been associated with the drainage of glacial Lake Agassiz. I am wondering if the regional expression of this event over India is linked to a consequent abrupt southward shift in the ITCZ.
I see. Yeah, I mean, again, that's a good question. And in terms of how that event or how the cooling in the North Atlantic was sort of transported, or how it was manifested in this region, is still a work that people have been working on, and there have been model studies, posing experiments that people do, like put in fresh water, weaken the thermohaline circulation, and AMOC weakens, and there's a heat buildup in the Indian Ocean. ITCZ moves southward, like who was asking this question? Sorry, Oliveira is saying that ITCZ was shifted southward, and this sort of contributed to weakening of monsoon. Now, there's another school of thought who think, when they think that it was mostly, and this was not an oceanic phenomena so much, this was an atmospheric phenomena. So the cooling that happened in the northern hemisphere kind of weakened the heating. So, if we kind of simplify the monsoon concept and say, oh, it's this heating of the Tibetan Plateau, and, and then creating of that low pressure. So because of the cooling of atmosphere that was caused by this glacial Agassiz drainage, cooling in the northern hemisphere, that kind of weakened the low pressure that was built up in the on the Indian subcontinent, or on the Indian subcontinent, and that's why the monsoon was weakened. So there are two school of thought. One is the oceanic pathway, and the other one is the atmospheric connection. So yeah, I don't know. I mean, there are studies published in both southward extent of. I mean, both of them sort of lead to moving of ITCZ and consequently weakening of monsoon around the ocean too.
Thank you. Very good. So, are there any other questions? If not, maybe you all can join me in thanking Yama for her presentation, either using your little electronic clapping, or if you want to turn your microphone on, and thank her for giving up her time late in the evening. I just want to remind you, next week we have another talk by Rajiv Saraswat, and he's going to be talking to us about decadal to millennial variability in the Indian monsoon and global implications. So look out for your email and check online, and we'll see you all again soon. Thank you very much, Yama.
Thank you. Thanks. Bye.